started recording here. Okay, great. So I don't know if anyone checked out the video that we posted last week, but I think the audio might have been a little bit shaky. So I got this microphone. So if you want to give it a listen afterwards and let me know how it sounds, yeah, that would be great. I think we're officially ready to go live on Twitch at this point. So, okay. So today we're going to talk about a couple of different things. So we're going to start out by defining Lyapunov stability, which I heard you guys talked about briefly in lecture. Okay. We're going to talk about some energy-like functions after that and see how we could use those to build up this concept of stability. And we're going to finish things up by talking about a special case of one of Lyapunov's theorems. Okay. So just regarding some general content logistics for the class, we're going to release homework 2 later today. Okay. Oh, I think someone, oh no, he's in. Okay. So we're going to release homework 2 later today. This assignment is going to be 2 weeks long. Okay. Instead of just 1 week, but it is going to be a little bit tricky. All right. There's going to be some kind of challenging questions on there. So make sure you get started early. All right. Please ask lots of questions. Makes us very happy. Okay. So does anyone have any questions just about like general logistics things, where we are in the class, what's going on, or how are we doing? Okay, wonderful. So yeah, please just do let me know if you have any questions at any time. Just raise your hand, shout it out, whatever's good. Okay, so let's get started by talking about Lyapunov stability. All right. Okay, so I don't know if you guys remember, but last time, right, we sort of finished things off by talking about this concept of an equilibrium point, and we gave this very general, like, intuitive idea for what it means for something to be stable. Okay, so we said that, you know, if we have a system, if we have some system like x dot equals f of x comma u, right, the pair xe ue is an equilibrium point if when we plug that into our system dynamics, right, we get back 0. So 0 equals f of x e ue, right? Because since x dot is the time derivative of our state vector, we're saying that at an equilibrium point, the derivative is frozen, right? We're not moving anywhere. We're just going to stay exactly at that state. Okay. So we had this very general idea for what stability meant for an equilibrium point, right? So we said, if we start close to an equilibrium point, right, start close, and we stay close afterwards, that's our very general definition of stability, right? Equals stable. So we did that demo with the 2 points on the pendulum, right? We had said that at that lower point, right, if we start at very close to, you know, that lower position of the pendulum, we're sort of going to stay there, right? We're going to swing in some region around the lower point. But if we start at the upper point, it swings right down, right? So that was an unstable point. Okay. So what are we going to do to sort of formalize this concept more mathematically, right? How do we involve math? How to involve math. The age-old 106 AP question, okay? So here's what we're going to do, all right? We're going to think about the stability of a slightly different system, okay? So we're going to talk about the stability of x dot equals f of x comma t, okay? We're going to ignore the effect of that input for now, and we're going to say, all right, since we have this t over here, our system is maybe going to depend explicitly on time itself, okay? So we're just going to ignore input for now. Okay. This actually won't be a very big deal for us. We can actually come back to it later when we talk about control. And we'll say why this isn't really something that is very restrictive. Okay. So we're going to try and keep things nice and simple, right? We're going to try and keep our notation and definitions clean. So one assumption that we're going to make, let's assume that our equilibrium point xe is just 0. Okay. We're just going to keep things nice and easy for us and make sure our notation doesn't get super convoluted. Okay. All right. Once again, this assumption is also something that we could really work out in general. If we have an equilibrium point that's not 0, we can really just shift our coordinates, and this whole thing is going to be completely equivalent for us. All right. But for now, we'll just assume xe is equal to 0. So how do we know if this point is stable in more mathematical terms? Okay. So we'll define something called Lyapunov stability. So definition, Lyapunov stability. Okay, here's what we're going to say, all right? So I'm going to list out a couple of more mathematical terms, and we'll sort of break this down in just a moment with a diagram and then a little demo, okay? So we say that the point xe equals 0 is stable in the sense of Lyapunov. In the sense, very fancy sounding, sense of Lyapunov. Okay, and this is just abbreviated SISL for stable in sense Lyapunov. Okay, and we're going to say it's stable in the sense of Lyapunov at time t equals 0, t equals t0, if for all epsilon greater than 0, all right, we'll get back to that in just a sec. Oops, I've opened the keyboard. There exists a delta that depends on epsilon, all right, and that depends on our initial time t0 as well, such that the following is true. Which one?
Because in the slide, you put the delta dependent on epsilon, but the functions, I don't think it's add epsilon in the functions. It had t0 and something else.
There should be, yeah, there should be a delta dependent on epsilon and t0. So in some cases, it won't depend on t0.
Yeah,
that might have been.
I was confused because in the lecture slides it said delta. He kept saying it's a function of epsilon and t0, but the slide had delta.
Oh, so that must have been a typo on the slides then. Yeah.
No, he just kind of reversed.
Oh, okay.
Was there an epsilon in it at all? Yeah, based on what I wrote, he didn't have.
It should definitely depend on epsilon. Yeah. Yeah. Great point. Thanks. Okay. So what we're going to say is that if our initial condition has a magnitude or norm that's less than that value delta, then for all time, we have the magnitude of x of t is less than epsilon, okay? For all t greater than or equal to t0, okay? So if we have this condition right here, our point is going to be stable in the sense of Lyapunov, or Lyapunov stable, you could also say. Okay, so let's try and discuss what these different parts of the definition actually mean, all right? Let's get a little bit more of a visual perspective for what this is. Okay, so when I draw out this picture, just keep in the back of your mind that idea of start close, stay close stability, all right? This is really all that this definition is saying, just in much fancier terms. Okay, so let's try and sketch out what this definition is saying. So what I'm going to do is I'm going to draw this little region over here, okay? And then I'm going to draw another region going around the outside. Okay, so this outer region, let's just pretend that that's a beautiful, perfect circle right there, okay? That's going to have a radius of epsilon, right? And inside here, we have a region with a radius of delta, okay? So what we're saying is that if our initial condition for our system starts within here, right? Let's say we start with that initial condition within this region of radius delta, we're going to end up staying within this outer region of radius epsilon for all time, okay? So as long as we start within this inner region here of radius delta, that smaller region, our initial condition, we pick something, we're always going to be staying within this larger bubble of radius epsilon, okay? So that's this idea that we start close, right? That's our x0 is less than delta. We have stay close. All right, which means that x of t is less than epsilon. Okay, very cool. So do we sort of see how this sort of picture is contributing to this definition of Lyapunov stability? We start close, right? We start within some delta. We're going to stay close. We're going to remain within this epsilon. Do we see how that's sort of coming together to give us this definition of stability? Okay, cool. All right, so we're going to do a short demo now of Lyapunov stability, but I do need 2 volunteers. I'm sorry, I hate picking people out. I know, Pranath, we got you last time with the pendulum, but Daniel, all right. Amazing. Okay, Noosh. Okay, so who wants to be the equilibrium point and who wants to be the epsilon? You're really good at epsilon. Okay. Okay. So if you stand over here. Okay. So I'm going to be the trajectory. Okay. I'm going to move around a little bit. So what we're essentially saying is that Daniel is staying at 1 epsilon over here. Okay. He's fixed. And as long as I start somewhat close to where a nuge is, right? As long as I start within some delta, I'm always sort of going to remain some distance away from Daniel for all time. I'm sorry. But if he moves closer, so if you move in a little bit closer, I'm able to find another value of delta that depends on epsilon, such that even though he's now closer, I can now move a little bit closer to a nuge, right? But still ensure that I'm always able to stay some distance away from Daniel for all. So what we're essentially saying is that if a nuge is a Lyapunov stable equilibrium point, right? And Daniel is setting some radius epsilon, I'm always able to find some range around a nuge that I can start with so that I always stay closer to him than Daniel is. Okay? So that's our general idea of what Lyapunov stability is. If you want to give them a quick round of applause for our epsilon with our equilibrium. Yeah, check something like that.
So you're always able to make that smaller.
Yeah, so what we're saying is that if XE is a stable equilibrium point, right? For every value of epsilon, whether it's like 10 or 100 or 0.0001, we can always find some distance delta, such that if we start that distance away, we'll always remain within that outer bubble epsilon.
Oh, okay. So just like given, we can set like epsilon to be anything.
Yeah. Yeah, that's right. Can find a delta. Okay, wonderful. So there are actually a lot of stronger forms of Lyapunov stability than this, okay? So one thing that we notice here is that this doesn't actually guarantee us a convergence to the equilibrium point, okay? So stable in the sense of Lyapunov is not equal to convergence, all right? And we sort of see that from this definition up here, right? Because this was our x of t, right? That satisfied this definition of stability in the sense of Lyapunov, but it never actually converges to our equilibrium point at the origin, right? It just sort of swims in this outer radius for all time, okay? So it tells us that we remain close, but not that we actually converge to that point. Okay, so if we wanted to show convergence, there are a couple of more stronger forms of this idea of Lyapunov stability that we would be able to use, okay? So today we're just gonna focus on this more relaxed form so we could try some good examples. But on your homework, you'll see a couple of these stronger forms of stability pop up. Okay, wonderful. So do we have any questions about this general idea of Lyapunov stability, just this definition that we've covered here so far? How are we doing? Okay, cool. All right. So now we could sort of move on a little bit and talk about energy-like functions. Energy-like functions. Okay, and this might seem like a little bit of a digression from this idea of stability that we were just talking about, right? Like, what does energy have to do with this thing? But we'll actually see these two concepts are very, very closely intertwined, okay? All right, so one thing that we know about our definition of Lyapunov stability, right? We're requiring this bound on x of t. So Lyapunov stability, we need a bound on the magnitude of x of t. So if we wanted to try and apply that definition directly, right, we would actually need to know what x of t is, okay? So to apply it directly, apply our definition directly, we need x of t. But what's the problem with that, right? So we have this system, x dot equals f of x comma t, that is entirely nonlinear. So does anyone see any problems with needing x of t from this nonlinear system? Just, yeah.
Most of these solutions are not analytical.
Right. So we can't actually find a closed form solution in most cases to this nonlinear equation, all right? So we typically cannot actually find x of t, okay? So what do, right? Our definition directly relies on us having this x of t, but we can't actually find it in general. So we need some sort of way to essentially avoid this x of t entirely in our study of stability, okay? So we want to try and find another approach, maybe using these energy-like functions, to see if we could describe stability of a point, okay? So we want to describe stability without using this idea that we have a solution for x of t, okay? So we're going to try and sort of avoid this problem of solving the differential equation by talking about something called an energy-like function, all right? And I'm just going to sort of preface this a little bit by talking about a very simple physical system, okay? So let's consider the system consider the system that has a mass that's just oscillating on a spring, right? So we have a little spring over here. It's attached to our mass. We have mass M, maybe a spring constant K. And I'm also going to add this thing called a damper, okay? So if you guys haven't seen a damper before, it has a constant beta, okay? It's called a damper. This damper is essentially something that just applies, you could think of it a little bit like a frictional force to this mass, okay? So as this mass is moving, this damper is applying a force opposite to the direction of motion of the mass. It's proportional to its velocity, all right? So if this mass is moving super quickly, the damper force is going to be super high in the opposite direction. Tries to slow it down, okay? So it slows the mass down. Okay. So we know that if we have this mass, right, we stretch it out at some configuration, right? We let go, it's going to start like oscillating back and forth for a good while, right? We're sort of going to end up tracing out this pattern, right? We're going to go a little bit like that, right? But we know that eventually it's going to converge to its resting position, right? And that's all because of this damper right over here, right? It's burning up energy as we're going along, and it's making sure that this thing isn't just going to oscillate for all time, right? It's making sure that eventually it converges to its unstretched position, okay? So what's happening is our damper burns up energy. And since it's burning up all of this energy, right, our mass, it doesn't have an infinite amount of energy, right? Eventually that energy is going to go and drop to zero. When it drops to zero, it won't be able to move, right? The evolution of our system will be frozen. So eventually what's going to happen is energy drops to zero. Our system freezes. And we know that when a system is frozen, right, it must be at its equilibrium point, okay? So that means that it goes to its equilibrium point. Okay, so let's just sort of summarize what we said here, all right? We said that by looking at the energy of this system, right, and showing that it's always decreasing, or at least always less than or equal to zero, right, as we take that rate in time, eventually this thing will converge to its equilibrium point and just stop moving, okay? So what we said is that if energy is always decreasing, right? If I say like E is a letter for energy, right? This means that the time derivative of energy, E dot, is going to be less than or equal to zero for all time, okay? And we saw that when we had the derivative of energy less than or equal to zero, we got stability, right? We got stability, all right? We stayed close to our equilibrium point. To our equilibrium point. Okay. So something that's really important, right, is that this is something that we're able to do without actually directly solving the equations of motion of the system, right? We could just look at energy, take its first derivative, and see what's going on with that, and see if we can make any conclusions from there, okay? So we didn't need to solve the system, didn't need to solve, we just looked at energy. Okay. So what we're going to do now is we're going to talk about how we can generalize this idea to an arbitrary nonlinear system, okay? So our main idea of this section, here's what we're going to do. We're going to use energy. I'm going to put this in little quotes for now, and you'll see why that is in just a sec. We're going to use this energy to study stability of nonlinear systems, okay? To study stability of nonlinear systems. Okay, so what are some problems that we foresee with using this energetic approach? Does anyone have any ideas? What might be something that's kind of tricky? Yeah.
We might not know how far away we'll get from the equilibrium.
Okay, yeah, that's a good one. So problems. So one might not know how far away we'll go Okay, any other ideas? Yeah, Anya. Sure. Yeah, so two, we could have non-conservative forces, right? So that's forces that don't have anything to do with the source of some energy field, like gravity or something like that. So non-conservative forces. So it turns out we'll actually be able to take care of both of these things. But our main problem right here is that an arbitrary system, x dot equals f of xt, is not necessarily a physical system, right? Is not necessarily physical. Okay, so for these arbitrary nonlinear systems, right? Like if we had x dot equals sine of x, right? What does the energy of that system mean in that context, right? What does it mean for x dot equals sine x to have an energy? This thing isn't actually referring to any physical system, right? So what does energy mean for this? Energy. Okay. So what we want to do now is we want to describe energy for an arbitrary nonlinear system, okay? So we want to come up with a set of functions that act like energy, but for an arbitrary system, okay? But for an arbitrary system. Okay, so if we could come up with this energy-like function for our system, maybe we could use that approach of showing that its time derivative is always less than or equal to 0, right? If we could do that, then maybe we could show that it converges to its equilibrium point, okay? So we're going to use this concept called a Lyapunov function. So we have this thing called a Lyapunov function, and we abbreviate it by like v of x comma t. Usually in our cases in this class, it won't depend on time explicitly, but yeah, just know that it can. And this thing is going to be our energy-like system, or excuse me, our energy-like function for a nonlinear system, okay? So energy-like function for a nonlinear system. Okay. So does anyone have any questions about our motivation for this, right? Why this V is something that we need, why this is something that we're actually interested in finding? How are we feeling about this, guys? Good? Okay, cool. So what do these functions actually look like, right? What are the conditions for something to behave like an energy function? So we have two different possibilities, okay? So two possibilities slash classes for v of xt, all right? So the first possible class of functions that v of xt, right, our Lyapunov function can belong to is something called a locally positive definite function, all right? Locally positive definite function. All right, so this is abbreviated LPDF for locally positive definite function, so you don't have to write that thing out every time, okay? All right, so what we say by definition is that v of xt is a locally positive definite function if for some region around the origin, x equals 0, all that we have is v of xt is greater than 0 for all time. And at the origin itself, we have v of 0t is equal to 0, okay? So we say something is locally positive definite if for some sort of region around the origin, right, we have v of xt is greater than 0, okay? And at the origin itself, we have v of 0t is equal to 0, okay? So let me just sketch out a quick example for what that's like. All right, so if we have x over here, right, some like example of this. All right, let's say it goes down to 0 over here, right? We say that within this region, okay, this region, v of xt is locally positive definite. Okay, and we see that it is 0 at the origin, right? So 0 at origin, and it is greater than 0 for some region around the origin. Okay, so what do we think this has to do with energy, right? Can we think of any properties that this function has that an energy function shares? You guys just want to shout it out. Yeah.
You've got a local minimum at 0.
Yeah, sure. So we have a local minimum, global, yeah. So we have a minimum at 0. Minimum at 0, right? So if one of our states was, the distance of our mass from its equilibrium point, right? Its unstretched location, and the other state was the velocity of the mass, right? At that equilibrium point 0, we know that that mass really doesn't have any energy, okay? So we have a minimum at 0, right? What are some other properties, right? Is this something that's true for an energy function in general? Yeah. So it is also greater than 0 in general. Okay, so these two properties, right? This v of xt greater than 0 and v of 0t equals 0, right? Those behave somewhat, at least somewhat, like an energy function. Okay, so somewhat similar to energy. Okay, so remember, oh yeah, of course. Yeah, let me know when. Okay, great. Yeah, I'll give you guys just a sec to write this down. I know I went a little quickly there.
Sometimes I remember last semester we talked about energy of K.
Yeah, so it depends on where you define your reference point with respect to. So it can be negative in some sense, but you could shift that up by a constant amount. So yeah, we're a little bit loose with it here, but yeah, in general, these are properties that you'll see for energy. Yeah, that's a great point though. Okay, cool. All right, so this was the first type of energy function that we had, right? But maybe there's something that's a little bit more specific, okay? A little bit more restrictive on what this function has to do, okay? So we have another type of function that we call a positive definite function. Positive definite function. Or PDF, okay? So before we were talking about locally positive definite, it only needs to have some properties in a small local region. Now we're talking about positive definite, right? It's going to have some special properties everywhere for all values of x, okay? So we say that v of xt is a positive definite function if there is a strictly increasing, I'll just abbreviate increasing with a little up arrow like that, okay? Strictly increasing function alpha such that the following three conditions are satisfied, okay? So first, we're just going to start off by having that same constraint, right? When we're at the origin, our energy function should be 0, okay? So v of 0t equals 0. Same as before, all right? Now, in the second condition, we're going to use that strictly increasing function alpha, all right? We're going to say that for all values of x, we have v of xt is greater than or equal to alpha of the magnitude of x, okay? So remember, alpha is not a specific function. We're just saying that there should be an alpha out there, right? There might be a possible alpha for which this is true, okay? And our third condition will be that the limit as p goes to infinity of alpha of p is equal to infinity, all right? So as we send p off to infinity, alpha should blow up to infinity as well. Okay, so these three conditions are a little bit more abstract, right? Maybe a little bit more difficult to visualize. So what might one of these positive definite functions actually look like, okay? We'll sketch it out once again on a coordinate grid, all right? And a classic example of this is just a parabola, right? Like y equals x squared. All right, so if we take 1/2 of parabola, say v of x equals x squared, that's x. We're just considering like a simple scalar case in this case, okay? So we know that this thing is bounded below by this strictly increasing alpha of x, okay? So this alpha, this linear function, is always increasing for all time, right? Its derivative is always greater than 0. And we know that v of x equals x squared is always going to be greater than this alpha of x, okay? So what we can do in this case is we could sort of figure out, or here, this will sort of be like ax squared plus da 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 or something. Okay. So we can essentially figure out that we could bound this thing below by a strictly increasing function alpha of x, right? We see that as p goes to infinity, alpha will go off to infinity as well, right? And we see that our function v is 0 at the origin, all right? So when you see positive definite function, you could sort of think about these quadratic functions, all right? It's usually a pretty good thing to reason about. Okay, so do we have any questions about what a positive definite function is, all right? Now I'll just write down here, this is a stricter form. So stricter form of an energy function. All right. Yeah.
There's no restriction on the amount of TBC and units.
Like
it doesn't have to be
oh no, yeah. So V can really yeah, like V can totally like squiggle around up here, and that's going to be totally fine. Yeah, as long as we could bound it below by some strictly increasing function, we're all good. So there's another class that's decrescent functions that, yeah, do tend to bound that. Yeah, great question. Yeah, and it doesn't have to be linear, right? So it could be quadratic itself or some other strictly increasing function. As long as it's always going up, alpha is all good. Yeah. So yeah, that's a great point. Thanks. So alpha is not necessarily linear. Yeah, so as long as you find some alpha out there that satisfies what you're looking for, you're all good. Yeah. So it just needs to be some increasing function.
So is linear the lowest possible kind of
so you'll see in your homework that if you bound it below by a linear function, you'll actually get some special properties for exponential convergence to an equilibrium point, which is why we like linear functions. Linear functions are also, yeah, they're just kind of nice to work with. They're pretty simple. Yeah, so where you can try and bound it below by a linear, but otherwise something like quadratic or some other increasing function. Yeah, great question. Okay, so let's do an example problem. All right, problem 1. So this is going to be off of the discussion worksheet that is on our class website. If you guys want a paper copy, I have them up here, okay? So what we're gonna say is let P in our n by n matrix be diagonal and have all positive and real eigenvalues. Okay? So we're going to say P is going to be the following matrix, right? So we're going to have some lambda 1, lambda 2, all down the diagonal, lambda n, right? Zeros everywhere else. It's an n by n matrix. Okay, so just remember eigenvalues in this case that we're giving you, they're going to be positive, they're going to be real, okay? So what I want you guys to show is show that V of x equals x transpose px, where x is an n-dimensional vector. We want to show that this function V of x is a positive definite function, all right? So what you're going to go and try and do is try and show that this special function over here satisfies these 3 conditions that we just talked about, all right? So I just want to point out this problem over here will be really, really useful for your homework 1, okay? Or excuse me, your homework 2. So this will be a result that you're actually going to be able to apply directly on your homework, okay? All right, so I'll give you guys 3 minutes if you want to go ahead and at least like, get a little bit of a start on this problem, all right? So if you have any questions, just raise your hand and I'll come over and yeah. If you guys want to turn and talk to the person next to you as well, that would be great. All right, we're just going to give it one more minute and then we're going to come back together, okay? Okay, so does anyone have any ideas about where we want to start with this question? All right, just for the sake of time, we're just going to prove that second condition. All right, I think this is the toughest one to prove, that X transpose PX is greater than or equal to some alpha magnitude of X or some alpha. Okay, do we have any ideas about where to start? Yeah.
I just chose, well, to start off, you can turn this into a simple quadratic and all the variables by saying b equals lambda 1 x1 squared. Plus
Yeah.
all the way down.
Yeah, so if we actually calculate out the value of this v of x, right, we could show that it's equal to lambda 1 x1 squared plus lambda 2 x2 squared plus lambda n xn squared. All right, so where do we go from here? Daniel, I think you had your hand up as well.
Yeah,
Okay, great. Yeah. So how will we end up isolating this x out of this expression over here? What will we do? We could try and form some inequality, maybe, right? What do you think?
I mean, I haven't done
Okay. Yeah, problem.
I mean, I know what I'm doing. So.
Yeah, okay. So do we have any other ideas? Yeah, Aaron.
Like lower bound quadratic by just the minimum of the lattice.
Yeah, that's perfect. So if we define some lambda min, right, that is the minimum of lambda 1 through lambda n, right? This is going to be greater than or equal to lambda min times x1 squared plus x2 squared plus xn squared. And then, Khaled, I saw you had your hand up as well. Do you want to finish this off? Or
Yeah, I was just gonna say. I was gonna say the max, but
yeah, it's just going to be the other way around. Yeah, perfect. Okay, and it's x1 squared plus x2 squared plus all the way through xn squared. This is equal to lambda min magnitude of x squared. All right, and that's a quadratic function in the magnitude of x. So this function is strictly increasing. All right, so therefore we found our alpha of magnitude x that is a lower bound for this v of x function. All right, so that proves that nice second step of this positive definite definition for us. Okay, so once you have this alpha of x, finding the other two conditions is going to be a little bit easier. Okay, so just for the sake of time, we won't talk about those here, but I will upload those in the solutions later. Okay, so do we have any questions about why we chose this minimum eigenvalue, why we were sort of going for this lower bound over here? What are we thinking, guys? Good. Okay, fantastic. Oh, yeah. Yeah. So lambda min is greater than 0, right? Because all of our eigenvalues are greater than 0. And then if we plot, right, like that on our x-axis, this essentially becomes like a quadratic function, right? Lambda min, yeah, just like that. Is it good? Great. Okay, so we're going to finish things off by talking about the basic theorem of Lyapunov. Basic theorem of Lyapunov. So if we have some time left over, we'll do one short practice problem about this, okay? But we're just going to try and nail down the definition of what this theorem is first and foremost, okay? So remember, we had all these different things about energy earlier, right? We said that if E dot is less than or equal to 0, then maybe we can conclude stability, right? Maybe conclude stability. All right. And now in the previous section, right, we identified all of these energy-like functions for these arbitrary nonlinear systems, okay? So what we're going to say now is we're going to use these ideas, right, of these positive definite, this locally positive definite Lyapunov functions to try and make some conclusion about the stability of our system, okay? So this brings us to the basic theorem of Lyapunov. Basic theorem of Lyapunov. Okay? This is also called the direct method. And we're only going to state part of it here, but there actually are a couple of other parts that help you conclude higher versions of stability, right? More strong versions. But what this more simple version is going to say is that if we have some sort of function, okay? So let me write this in a different color here. Yeah, there we go. Sure. Okay, so what we're going to say is, imagine we have some function v of xt that is locally positive definite, all right? LPDF. So one of those energy functions we were just talking about, right? Now, what we're going to say is that if for some region around the origin, right? We're going to assume that origin is an equilibrium point, xe equals 0. We have the following condition. We have the derivative of v of xt subject to the dynamics of our system is less than or equal to 0, right? Subject to x dot equals f of xt. Then we can conclude xe equals 0 is a locally stable equilibrium point of x dot equals f of xt, okay? So we're saying that if v is one of these energy-like functions for our system, right? And subject to the constraint of our dynamics, we can show that v dot is always less than or equal to 0 in some small region around the origin, right? We can conclude that we're going to be a locally stable equilibrium point, right? Which means that as long as we don't go too far away from our equilibrium point, we're going to be stable, and we're going to have that, you know, sort of keeping in the region of the equilibrium point condition, okay? All right, so this is our basic theorem of Lyapunov, and it uses our energy idea to conclude stability without knowing x of t. Okay, great. So do we have any questions about this definition over here? Okay. How are we feeling about this theorem that, you know, we don't actually need this x of t, we could just use energy to study stability instead? What do we think? Do we like it? Do we not like it? Okay, somewhere in the middle. Okay, wonderful. So I just want to make one quick remark, all right, about something called a derivative along a trajectory. Along a trajectory, all right? And that was sort of this idea over here, right? We're taking this derivative v dot subject to the constraint that x dot is equal to f of xt, okay? So the derivative along a trajectory is when we take a derivative, and we use x dot equals f of x, right? The dynamics of our system, xt, as a constraint, all right? So how do we actually find the derivative along a trajectory, right? To make sure that this function is decreasing and at the same time respecting the dynamics of our system. Yeah.
Chain rule.
What's up?
Chain rule.
Chain rule, yeah. So we have this function v of xt, right? So if we want to calculate d dt of this function, right? This is a multivariable function, right? So what are some terms that we're going to need? You have any ideas? We want to calculate the time derivative of v of xt using chain rule. Does anyone remember what chain rule is?
First, take the derivative of v itself.
Yeah. So like dv dt, like that? Yeah.
Then multiply v by the derivative of x inside.
Yeah, so that's almost what it's going to be, right? So we're going to take the derivative of v, partial derivative, with respect to this first variable, time, right? But we know x is actually a function of time itself. So we have to apply chain rule to figure out this next piece of the derivative, all right? So what we're going to do is we're going to add on dv dx to see how it changes with respect to x. But we know x is also changing with respect to time. So we need to multiply this by dx dt, okay? So this is from chain rule, right? And what do we know now? Okay, so we want to substitute this sort of condition, right? X dot equals f of xt into this expression. Well, we see we have an x dot right here, right? Dx dt is just x dot by definition. So if we do dv dt plus dv dx and substitute in f of xt, this is the derivative of v along the trajectories of x dot equals f of xt, okay? So all that we're saying is we're just adding in this extra constraint that we're actually using our dynamics when we're taking this derivative, all right? So that makes sure that when we take this derivative, we actually do it respecting the physical laws that are governing our system, all right? So we're gonna jump very, very quickly into an example problem of how we might show Lyapunov stability, all right? So our problem here will be that we have a system that's described by the equations. Theta double dot is equal to, let's see, negative, let's call it A times sine of theta minus some beta times theta dot, all right? And we have a candidate Lyapunov function for the system, right? One of those energy-like functions that is a function of theta dot. It's equal to the following. 1/2 theta dot squared plus a times 1 minus cosine theta, all right? Maybe we've sort of come up with this from an energy-based approach, right? So this is actually the equation of motion for a pendulum, and v is actually the energy of the pendulum right over here, all right? But for a more arbitrary system, maybe we use some other method. We just thought, okay, this looks like a good function. We hypothesized that it decreases, okay. So what I want you guys to try and show is show that for some values of theta and theta dot, we have the following condition, all right? We want to show that v dot theta dot along the trajectories of the system is less than or equal to 0, okay? So why don't you guys take 1 minute and see if you could get started on that, and then we'll review the solution super, super quick before we let you go for the day, okay? All right. So just remember this, along the trajectories just means that you substitute your dynamics into wherever you see a theta double dot in your equation, okay? So if you get theta double dot, substitute. Yeah. Why is the partial derivative added? Oh, yeah. So in terms of the proof of that, I don't quite remember it off the top of my head, but it's really just that if you try to think about it like a vector, right? That this v is maybe like a vector valued function in space. In this case, it isn't, right? It's like we're taking the different components of that vector that add into getting our overall derivative. So first we take a little component that takes, how much it's changing with respect to time. Then we add on that extra component that shows how much it's changing with respect to x, and then multiply that, scale it up by how much that's changing with respect to y prime. And when we add those two together, right, that gives us our total vector that tells us how much v is changing. Does that make sense? In this case, v is not a function of time. Yeah. Okay. So what you're going to do in this case is just take the derivative more like traditionally. We don't actually need to use like this formal definition over here. Okay. All right. So I think it is 2. So I will just review the solution for this super quick. All right. Sorry, we kind of got a little pressed for time here. I'm first going to take the derivative of this using product rule. Okay. So we're going to get a theta dot multiplied by theta double dot. And then in the second term, I'm going to get a plus a times, I believe, a sine of theta times a theta dot. All right. We're just using normal differentiation rules. And then I'm going to substitute in my dynamics. Substitute dynamics. And that's going to give me a theta dot times, we have our equation up here, negative a sine of theta minus beta theta dot plus a, let me move this over here, times theta dot times sine of theta. So we see right here, this guy and this guy are going to cancel out, right? That leaves us with negative beta times theta dot squared, okay? So we're sort of distributing this in there, all right? So beta was a positive number, all right? So will this thing always be less than or equal to 0 for some sort of region around the origin? What do we think? Yeah, right? So this is less than or equal to 0 for some region, which tells us that xe equals 0 is locally stable. All right. So I know we did rush through this example a little bit, but in general, you're going to take this process of getting your Lyapunov function, showing its locally positive definite or positive definite, and then taking its derivative and showing that that's less than or equal to 0. Okay. So if you guys have any questions, yeah, I'll stick around afterwards. Please, yeah, do let me know if you guys have anything that you need. And yeah, I think we'll call it there for today. Thanks for coming.